Have you ever wondered what causes gravity, radioactivity, what keeps atoms from exploding, or more? Well, fundamental interactions, which are also known as fundamental forces, are everywhere and are the four basic forces that govern how objects or particles interact and how certain particles decay.
These forces include gravitational, electromagnetic, strong and weak nuclear forces.
The gravitational force is connected with the curvature of spacetime, while the other three are discrete quantum fields. Now, let's learn more about these fundamental forces. The strong force, which, as you can guess, is the most powerful of the four forces. It is the force responsible for keeping the atomic nucleus together in spite of the intense repulsion of the positively charged protons for each other. Although it is strong, it has a very short range and is restricted to an operating distance of about 10 to the negative 15 meters, about the diameter of a proton. The strong force acts between quarks, the elementary component of all subatomic particles, including protons and neutrons.
A type of particle called a gluon is what mediates the strong force between the quarks. These particles cause quarks to be produced, and if quarks begin to separate away from each other, this helps glue them back together.
While the quarks are close together, they don't experience much force, but as they move away from one another, the forces between them increases rapidly, which pulls them back together. And in fact, in order to separate two quarks from each other completely, it would require even more energy than what a particle accelerator can provide.
The weak force is an interaction between subatomic particles at small distances less than the diameter of a proton. It is also the force responsible for radioactive decay and neutrino interactions. Particles affected by this force must pass within 10 to the negative 17 meters of one another to interact, and the probability that they will do so is so low even at that distance, unless the particles have high energies. It involves the exchange of intermediate vector bosons and is responsible for changing one flavor or type of quark into another type. This transmutation of quarks is what causes nuclear decays, such as beta decay. This fundamental force is necessary, as it is crucial for nuclear reactions that fuel the Sun and other stars, and is also necessary for the buildup of heavy nuclei. All subatomic particles experience weak force, but electrons do not experience strong force. Another fundamental force is the gravitational force, which is purely attractive.
This force has an infinite range, yet it is the weakest in magnitude of all the other fundamental forces, with a strength of about 10 to the power of negative 41 at the scale of quarks and 10 to the power of negative 36 at the scale of protons or neutrons.
Although it is the weakest, it is the most dominant force in the universe for shaping structures including galaxies, black holes, and smaller scale experiences like falling objects. This gravitational force keeps planets in orbit around the Sun, and the Moon in orbit around the Earth. Using Einstein's theory of general relativity, gravitation can be defined as the curvature of space-time around an object of mass.
This curvature causes a path of least energy, which is towards the other object of mass, and this explains the attractive force which draws two masses towards each other.
The theory of general relativity also explains the changes in mass configuration which can produce gravitational waves.
Another one of the fundamental physical forces in the universe is electromagnetism. The electromagnetic force is the interaction of particles with an electrical charge and is shown through the forces between charges, which is called Coulomb's law, and the magnetic force. Both the magnetic and electrical force can be summarized using the Lorentz force law.
This electromagnetic force is what holds atoms and molecules together.
It is so dominant that the other three fundamental forces of gravitational, strong, and weak forces can be considered negligible as determiners of atomic and molecular structure. Similarly to the gravitational force, the electromagnetic force is a force of infinite range. This force explains several phenomena, such as the various aspects of electricity and magnetism, visible light, radio waves, and friction and surfaces.
All four of the fundamental forces involve the exchange of one or more particles. These are called the exchange forces. For the strong force, its exchange particle is a gluon. For electromagnetic force, its exchange particle is a photon. For the weak force, it is W and Z, which are intermediate vector bosons. Finally, for gravity, its exchange particle is a graviton. Exchange forces can be attractive or repulsive, but have a limited range depending on the force. The maximum range is determined by the uncertainty principle, since the particles that are involved are created and exist only in the exchange process, which is also called virtual particles. In order to be able to interact, every particle must behave as either a boson or a fermion, which are the two classes of particles.
Both bosons and fermions can experience this exchange interaction by either remaining unchanged and staying symmetric or changing its sign, which is antisymmetric. For fermions, the interaction is called Pauli repulsion and is related to the Pauli exclusion principle. For bosons, however, the interaction is an attraction that causes identical particles to be found closer together.